Multiclass learning from contradictions. We focus on the problem of learning with high-dimensional data, especially when access to labeled samples is limited. Most algorithms designed for such problems involve inductive settings. One approach specifically designed for high-dimensional problems uses large margin classifiers. A popular example is the multiclass SVM or MSVM introduced by Kramer and Singer. Unfortunately, the performance of most such approaches is suboptimal when the label data is limited for high-dimensional problems. This motivates the need for advanced learning settings. One such setting is learning from contradiction or universal learning, where the algorithm can exploit unlabeled samples from the same domain but belong to none of the classes being learned. For example, consider the task of gender classification from images. Here the labeled examples are male and female faces, while the universal samples can be face images that are neither male nor female. Under the universal learning setting, we then build a classifier which explains the training samples well and also maximizes the contradiction on universal samples. The idea was originally introduced for binary classification problems and has been shown to be very effective in high-dimensional settings. This paper extends universal learning framework to multi-class setting as presented in definition 2. We show that maximum contradiction for MSVM can be achieved when the universal samples lie close to the decision boundary of each class. We use this insight to formalize multi-class SVM for universal settings called MUSVM, where we use large margin loss, same as MSVM for training samples, and delta insensitive loss for universal samples. We derive several useful properties for the MUSVM formulation and show that MUSVM is solvable through any state-of-art MSVM solvers. We also analyze the sample complexity for PEC learnability of MUSVM using the most widely adopted capacity measure for multi-class problems, the Natarajan dimension. We show that the sample complexity for MUSVM is smaller than MSVM. This indicates that MUSVM can achieve better test accuracies for problems with high-dimensional limited labeled samples. Our empirical results confirm this by demonstrating 20% accuracy improvement over MSVM. The proposed HOP visualization method provides further insights into the performance. Finally, we derive a new computationally efficient span bound for leave-on-out error that also allows for efficient model selection. Our results show up to 4 times speedup against 5-fold CV and over 100 times speedup against leave-on-out model selection. In conclusion, we formalized universal learning for multi-class learning, provided several useful properties for the formulation, analyzed a sample complexity for PEC learnability, and derived an efficient analytic bound that also enables model selection. Finally, we provide exhaustive results in support of our methodology. Additional details are available in the paper. Accompanying codes are provided in the video description below. Thank you.